Hello everyone. So I'll start with the auditory evoked potentials data analysis and processing using the MATLAB with EEG lab and ERP lab. So what we will do is first we can obtain these EEG lab and ERP labs as we can obtain that in the website, so we can just download it. And the most important thing about this is the ERP labs, it has to be copied inside, it has to be copied in such a manner that it should be placed inside the plugins of EEG lab. And so here we have the ERP labs pasted inside the plugins of EEG lab folder. After that, the next thing which we have to do is we have to set the path inside this MATLAB. So here we go inside here this option called as set path, and there we add this add with subfolders the EEG labs. This particular folder we will just open it, so that all the plugins along with the functions, all the pop-up functions, all the different everything will be added into this, and then we just save it and close. So this is an important step before starting up with this EEG lab and ERP lab. Then if you just after saving it, if you just put EEG lab like that, and it will start running like it starts working. So it should start coming like this, and you will get the graphical user interface. Then there are, as I said, there are various plugins that are there for this particular software. They're like, we can have various importing functions for importing the different types of EEG files. So here in this files we can have this EEG extensions, manage EEG extensions. Okay, so in that we can have various options, like we can give the different plugins, we can download and we can keep it inside our plugin folder of EEG lab. So for now we wanted the Neuroscan's systems EEG import format, so that has been given over here. So here we can just directly import the CNT file using this GUI. So we just click that and we can have the so I take my AEP data in this. So this is a CNT file, it's a continuous data file that has been obtained from the Neuroscan system. So we can just directly open it. If you open, it will ask like which is the number of bit you want and everything. So you just go with all the default parameters that has been given. So it will give an auto detective itself. So we can name it however you want. So we can, I just write it as AEP. And then if you have a different name than any subjects you have, or you have a different any IDs or something like that, you can just paste in that manner itself. So you will get the data set in this. We will now we have imported the data inside this EEG lab. So over here we can see that the epochs are just one, because we haven't divided our EEG into epochs. We have just the whole EEG bunch of data that has been there. So here the events are, these are the number of events that is there. Events are nothing but the triggers that we have given, like for example now in case of AEP we have the audio triggers that is being given. So we can visualize that the triggers also. I'll just show you that later. So here we have the start and the end time. Like first it starts it starts from 0 to 27 seconds. So here this is the total time length of the experiment we have conducted, and then the data size, everything. So we can give this addition externally, we can give the channel locations, or sometimes the EEG lab itself will have all these channel locations there inside the file itself. For example, in Inobio systems or OpenBCS systems and all, we can give we have to manually do all the importing the data or the events based on the channel size, channel number, etc., or the columns number, like that. So I'll just go with this CNT file for now. So next I'll just show you how the plots look like. So here in this plot session we have the channel scroll data. In this place, we can see how the different these are the 64 channels that are being recorded, and then it's we can change the axis, like this is for 5 seconds like that, so we can make such a manner that we want 30 seconds per to be seen. So here if you see, here we have all the triggers, these are the triggers, these red lines that is there, those are the triggers, and see here we can have a lot of artifacts and all can be seen. So we can manually also reject all this by just selecting like that, or else we can just do it using the the EEG lab analysis, like the artifact rejection protocols. Here we can change the amplitude, or like we can make it however smaller, bigger you want, and here we can scroll the data from left to right, like we can just move about us and see how the data looks. So this is just to see, and you have to think, you have to check, what you have to check mainly is the what is the trigger number over here. So there are two different here, this 2 is our trigger, like the AEP triggers, the 2 is our number, the trigger number that we have recorded over here. So the next step is like the initial pre-processing. Before doing any analysis, we just wanted filter to be done, just a small filter called as the notch filter. We will just there are various filters like the FIR filter or IIR filters. We will take this notch filter over here, and usually for us we will take 50 hertz of a notch filter and then just apply it. So here while doing itself, there will be in this command window, there will be how the processing is being done, how far it is being done, it is all shown, and these are the equivalent commands that we get. And this is it itself gives what the data name you have to, data set name you wanted, it will only give, or you can change according to your wish. So here these are the equivalent this is the equivalent command window. So after doing all these steps, we can just copy all these and put into our scripts. We can make the scripts based on that. So I'll just work with this GUI for now. So here we can give this channel locations. Okay, so for that we just go to this edit, and here we have the channel location. In this channel location, it's all the default, it's all like the 64 channel data, it's like all the default that has been present. So we can just go with it. And then here we have the different electrodes and its positions and everything it has been given, and for that, for 64 69 channels, how it looks and everything is we can just look about. Okay, and then this is all the default, just put an OK, so it will give the channel locations will be fed. So here we have all the channel locations done. Okay, now next we have to do is the event list. So what is this event list? Now the system, this MATLAB, it doesn't know like whether what is the event name, how should it look and all, it doesn't know. So for us, we know that okay, the triggers that are coming as 2 is our they are the events for us, but then the system should be given, we have to give it the input to that system that okay, this 2 is for the triggers. So we just go to the advanced protocol. So here we have to, this is the event name. So here this 2 is the event name that we had given in the, that is there in the continuous data file, and we just name it as 500 it will be 1000 hertz, and then we assign a number called as this bin. Based on this bin number only, we will be able to do the bin operations, or we can visualize whatever waveforms or ERPs which we require based on this bin numbers and these inputs we give over here. So we just we just write accordingly. So based on what triggers, based on like for AEP it's just one trigger, so we can just give one line like this. Yeah, so we can just update update the line. So this is how it gets updated, and you can just save it also. Later on you can use the same event list. So just save it and then we can apply it. So what happens is all these then all the numbers which was named as 2, it will now become bin 1s, or it will be named in that manner. So that is why we are doing this particular step, and we can this is called as the event list. Creating the event list. This particular step is called as creating the event list. Now next what we have to do is the epoching. Now as I told, it's like from 0 to 250 seconds the whole data is being given, but I require for a particular trigger I want pre-stimulus, I want some 50 milliseconds, and after that I want some 200 millisecond, like that. So we can just decide our time frame of how far we want all this, and that is called as epoching. So here we can create the epochs, we can extract the bin based epochs. So this is how it looks, and then so we always keep a baseline correction because we wanted to know how the data looks before the trigger comes in, so that we will get a idea of how it looks and how the base correction is being done. And so we will take, for now in this AAP we just require from -50 to 200 milliseconds. So I just do in this time frame, or we can change it also if you want to 300, or I'll make it 250. So like that we can change however we want and then run it. So it runs all the data. So it creates the event list. So this is how it creates the event the extract the epochs. So after epoching, how does the data looks? So if I just scroll this data now, this particular data set, for this data set, so here we see this is the bin values. These are the bins which was being assigned for this. So here these are all the artifacts that would be recorded. So what we will see is, I'll just show you how does one epoch look. So I'll just show one epoch, how does it look. So here if we see, this is the trigger. From this trigger I want just so it will for all triggers it will show like this, but then we wanted from -50 to 250. So I had just did that extracting the epochs. So this is how it looks. This is how the one epoch looks. So for similarly there are nearly 120 events that will be there. So there will be 120 epochs that will be created in this manner. For this further, if you do some artifact rejection and everything, some of these epochs and all will be reduced. It will be removed due to the artifacts present. So those now all these ERPs and all, it comes in so microvolts, in that range it comes. So just one epoch, if you visualize, if you want to see how one epoch or one how the waveform of one epoch looks, it will be very, very less. So for that reason only, how many ever events are there, we average all together that and then obtain. That's why we have any experiment if you do also, we don't do just for one trigger, for just one tone we don't do. We do for some 120 triggers or 150 triggers or sometimes even 1000 triggers. So it depends upon the experiment as such. So next I'll just do the artifact rejection. So artifact detection first we will do is using this threshold, voltage threshold. This is the most commonly used threshold artifact rejection method that they have used. Now what we have to do is, in this there are so many channels. In this I want only these for 64 channels alone to be crossing this artifact rejection. The other channels, if you take, it will result in all the events to be rejected. So that's why I just take only till the 64, the trigger channels especially, and this EMG EKG channels and all, you should not select for artifact rejection, because it will reject the whole data set, like all whichever data we require, it will all take off. I mean, it will just reject off all those things. So we just take only the first 64 channels, and here we have the time period from 200 yeah, so it will be from minus 50 to 250 millisecond. And then the voltage limits, as I told you, always the artifact rejection, it will take only from minus 100 to plus 100 microvolts. So this particular we can change accordingly to what you think the voltage limit should be. So mostly it will be minus the 100 to 100 alone, and then we just do the artifact rejection. So here if you see, yeah, see this here, the red colored, this selected channels over here, they are the rejected ones. Here this red colored ones, they are the rejected categories. So we can just check how many of them are being rejected, how many are being accepted. We can check in the command window. So over here we have selected so many channels. In this channel, almost 125 of them are being accepted, which means that in that particular voltage range, for these particular channels alone, these many so these 125 events or the triggers are being or these many epochs are being accepted, and 18 of them are being rejected. So this usually it will be like 80-20% like this only it will be, because there will be a lot of artifacts as I mentioned. So then what happens is, if you as I told you, if you do that trigger channels, if you select then the whole set of all the triggers will be rejected. For example, this whole of 143 epochs would come in the rejected range. So that should not happen. So that's why we don't take the trigger and EMG EKG channels and all. So over here we have to we can just, I'll just show you how does it look. So I'll just take 20 epochs. Over this 20 epochs, see all these yellow colored things and all are been in the reject range. So it's obviously seen that there are a lot of noise in this region. So that's why it is in the reject. We can reject all these channels. So I just do an update mark. So what it does is it updates. Okay, it will take that. Okay, these channels are the ones which have to be rejected. So we can go to this tools, and then we can just select this inspect reject data by eye, and then we can just mark this reject channels. And so what happens is all these channels, as I shown, that all the yellow colored channels, it all will get rejected. So here if I do just this reject, it will ask again and we can just reject it off. So if you see over here, see over that 125 over 143 events, only 18 of them were being rejected. So all those 18 trials are being rejected, like that it will show, and then it will create a new data set and we just save it in this format. So this is how the artifact rejection has been done. Next, what we will do is we have to do the filtering again. So because even after we didn't do any filter while acquiring the data, we have done some filtering options, but even during the data processing also we need to do all the data filtering steps. So we will do the data using this Butterworth filter. So we usually take from 1 to 30. Usually this is the range in which we do the bandpass filtering. If you want, we can change the order of the filter, or we can change the upper limit or the lower limit, like it can be minus 0.1 or it can be more than 30 also. So it depends on the what kind of epochs you are taking, or what kind of AEP or VEP, whichever ERP we take, it depends on that. So we just apply it. So as you apply, you will have the filtering being done. So after these filters, now we have totally 125 epochs are being there. Now these 125 epochs I want to be averaged all together and to obtain the ERPs. Now each of these time epochs we have to together, average together and get one particular waveform. That is called as that is this averaging step. So here we do this compute average ERP, average DRPs. So when we do that, we do for this 7th data set. So the 7th data set will have 125 epochs, so those we can do, and we can do any filter spectrum analysis. So if you want to do the total spectrum FFTs and all etc., we can do it, and this particular option should be selected because we don't want any of the artifact rejected epochs to be average. So this particular, it will exclude all the epochs that has been rejected by the artifact rejection. So then if you just run it, this is just a heads on, like it's just giving that we the EEG lab and ERP lab, it has to be synchronized. For that purpose it shows. But even if you don't do the synchronization step also, it will give the proper result itself. So over here, yeah, so we just save it wherever you want. Okay, I'll just name it as a AEP demo. Okay, so I just name it in this manner. So we can just save the ERPs. We can save this ERPs in this format, and we can. So as you do that, here we have the ERPs being produced over here. So before doing all those steps, this was the first importing the AEP. Then next we did the notch filter, and then we did the event list creation. Then we did the epoching over in this place, and then we did the artifact rejection. Then we just removed all the rejected data, and finally we did the lastly we did another bandpass filter. So these are the steps, sequential steps, and this particular, in this data set we did the averaging and we did the ERP. So this is the ERP set that has been made over it. Okay, next we want to plot how this does it look. So here we have the plot ERPs. In this we can this is how it looks. So here we have the time range from -50. So first we did the epoching from -50 to 250. So that is why it looks like this. And here the channels and all, we don't require the whole of this trigger channels and everything. So we just remove all these channels because it is not needed for us. We just require the other channels, and we can obtain the topographic, how it looks in the head. In that way itself we can obtain this. And as I told you, always we have to check this negative up for this N1 data. So then I'll just do topographic. Here we can have different style in which we can have the waveform. So I'll take a topographic and I'll just plot it. Yeah, so if I plot it, you will get the how it looks in the head. Like that itself we will be getting the data. So this is how it looks like for so here these are the frontal, this is the frontal electrodes, this is the nose side electrodes, or the anion nascent side, this is the anion side. And over here this is the temporal lobes. Here we have the frontal, these are the frontal part, and this is the parietal, and finally this last level here we have the temporal the occipital lobes. So mainly, as I told you, the AEPs will have in the frontal as well as in the temporal areas. So I'll just show you a particular data set only. For example, this mostly we check all the midline electrodes and this temporal electrodes and all usually. So if you just click one of this, we will get a large version of the thing. So as I told you, I have made it in the negative up, as a negative up I have done. So here, as I said, here this particular peak, that is clearly an N1 peak. This particular peak, it's clearly the N1 peak. The one which precedes the N1 peak, that is called as the P1, and the one which comes the next of it here, this particular peaks over here, that is called as the P2 peak. So this is the this whole area is called as the LPC complex. So this will be there in all the auditory, even if you do an MMN also, you will have this particular data. So this is a classic example of a AEP. Okay, so like that we can visualize for each electrodes, each and every electrodes we can visualize the similar things. So for example, if I want to check this, even in this also you can open it. uh, if you open it, so here we have the peaks obtained over here as well. So here we have, this is the proper N1 peak. Yeah, so it is correctly at 100, so this is the N1, and here we have the P1. The preceding one is the P1 and the next one is P2, so here it can be P2. Okay, so like that we can visualize for each channels like that, and then we can do some and if you see from here, this is the frontal and this is the occipital, that is from here to here. So what happens is there is a proper dipole inversion that has been taking place. From here, however it looks, it's the exact opposite it will be there in this. So it says that okay, the brain is also acts like a dipole. It's just indicating that thing. Now if you want, this is a topographic analysis kind of thing. Now we can have it as a individual waveforms also. In that we can do some statistical analysis also can be done. So I'll just take these 3 electrodes and some of the central electrodes. Yeah, this I'll just take this 5 electrodes for now, and we can have the standard errors of mean. What is the standard errors of mean? They are actually called as it's a statistical analysis which gives how accurate our data looks. So if thicker the band, it means it's a bit less accurate. If it is very thin, then it is called as it's more accurate data, we can say. So I'll just have 5 electrodes. So I'll just take in this manner. We can set how many our number of rows we want, how many columns we want. Always we can make it negative up also and positive up also. So I'll just make it negative up for our analysis, for this AEP analysis, and we can just plot it. So this is how it looks. So this gray portion is called as the standard errors of mean. So here we have the individual this one. So like that we can take for all the electrodes also. I just thought this is prominently we can see the N1 P1 peak and all. So that's why I just chose these electrodes. So like this we can do for other MMN P300 and even VEP also. I'll show the demo for each and everything. Another important step is, another thing is we can export this data. However these data are there, we can export it in the text format, or it can be in Excel sheet or ASCII file. However, in whichever manner you want, you can just export it. You can have the average ERP also. We can, if you want just the average ERP, you just select this. If you want for all the epochs, like for 125 epochs, for all the epochs, if you want, it will give in that manner. And then these frames per epoch, which means that from -50 to 250 millisecond, how the epochs, that is the epoch range, and for that range, for each epoch there will be 300 data points will be there. So that is what this frames per epoch mean. So that is just information that I missed last. So that is how we can export the data. That is a thing, and we can, all these images which we obtain, we can take it in the PDF format, or you can just zoom in out, anything you can do, all the options and all can be done over here. So this is about the AEP demonstration. So the next I will be giving you demos about the MMN P300 and the other ERPs. Yeah, so thank you.